next course will be given by Justin Simon and David Bommes. And Justin is an assistant professor at MIT. He did his PhD at Stanford with GeoGebas and postdoc at Princeton.
Yep.
Right. And David is an assistant professor at Aachen, and he did his PhD also in Aachen with Inequality and a postdoc at INRIA, Mediterranee in Nice, Sofia. And today they will talk about optimization algorithms and methods that are relevant for graphics problems.
Cool. All right. Yeah, thanks. All right. So it would probably help if I put my slides up there. Cool. So it's a pleasure to talk to you guys today. We're going to be telling you a lot about different techniques for optimization and geometry processing. I think the folks this morning almost did a little too good of a job helping us understand why optimization is definitely a necessary field for us to really consider seriously in the geometry processing world. And in fact, you guys saw some of the preliminary material that we were going to talk about today, which is very convenient for me, because now we can move pretty quickly through this. There are a lot of different names for basically the same idea. It's worth noting that oftentimes in geometry specifically, because a lot of us have background in differential geometry world, you'll see the word variational techniques. And essentially these things are synonyms. That variational techniques, and this is very roughly, are basically techniques that involve, defining some objective function which measures all the things that you want to be true about something you're trying to compute, and then trying to minimize it. Right? So variational calculus is all about, different techniques for doing this. And I think something, we were looking at tomorrow's talk titles, and there's like 3 different Swiss Army knives. And my hotel mate suggested that I contribute one more here. And I think it's actually true. We saw this morning that both of the talks this morning made really heavy use of these numerical algorithms for optimization. And for me, this really is a kind of a Swiss Army knife tool that if you have a really strong knowledge of the basics of numerics and optimization, you can get very far in geometry processing. And as evidenced by my own career, you get pretty far in geometry processing even with very little knowledge of some of the stuff that you really should know in the theoretical stuff. So when I talk about optimization, of course, in the most generic sense, what we're talking about is minimizing some function f of x, subject to a constraint that another function g of x equals 0, and a third function h of x is greater than or equal to 0. And of course, this is like the most generic language possible to describe an optimization problem. And we'll see, hopefully during the course of today's talks, that any number of different things can be essentially written in these 3 lines of description. And when I think about optimization for geometry processing, essentially, I feel like as a person that designs and works with these algorithms, really you go back and forth between 2 jobs in life. That on the one hand, something that's kind of interesting about optimization compared to a lot of other fields, like maybe algorithms would be an example, is that when you take algorithms class and learn how to sort numbers like 25 different ways, chances are you're not going to go home and implement these 25, quick sort and merge sort and bubble sort and God knows what to sort numbers and then kind of build all of these things into your code in different places or something. But I would argue that a really strong knowledge of very generic optimization techniques can get you quite far, even if you're just using these things out of the box. And so it's kind of a nice field that way, that even if you're not totally up to date with state of the art or don't feel like formulating your own homebrewed optimization tool, simply being aware of what's out there can get you pretty far. But on the flip side, in geometry processing especially, and I think we're seeing this more and more in some of the recent research papers, the types of objectives and the types of things that we want to minimize have very nice structure. And if you're willing to spend that extra time and design an algorithm specifically for the application you care about, you can get a lot of mileage. So today we're going to go back and forth between telling you about existing tools and telling you a little bit about kind of how to model with optimization and how to think about approaching optimization problems if you want to go home and roll your own solver here. Of course, our bias today is toward the geometry processing world. It's worth noting that, for example, at my school at MIT, there's an entire department that's basically for optimization. And so by no means in the next 2 hours are you going to, or hour and a half rather, I know, are you going to hear the entire breadth of what's out there in the optimization world. But our goal is really to give you a couple good ideas to think about and a lot of Google search terms. And hopefully from there, you'll be able to go home and formulate stuff for your own application to care about. So roughly today, I'm going to tell you a little bit about some very simple vocabulary of optimization, keep everybody on the same page, give you some very basic examples of problems that you might have seen elsewhere in numerics and not really thought of as optimization problems, and show that they can be written in this, minimize f of x such that g of x equals 0 and h of x is greater than or equal to 0. That really fits a wide range of different computational problems. And then I'll talk a little bit about sort of the two basic classes of optimization here. And David is going to really drive home some of the advanced methods that are out there. Things about dealing with inequality constraints and fancy algorithms. If I start building in constraints like my variables have to be integers instead of real value, what can I do? And so on. And depending on how much time you have left, we might do kind of a good cop, bad cop thing, and I'll come back and tell you a little bit about some of the modern techniques for convex optimization. So I'm going to kind of whiz through some of the vocabulary that I think most of us have seen before. Incidentally, I think y'all can probably tell I'm not the most formal lecturer. At any point, if you have a question, if there's a word you don't understand or something, you should just stop me, because I shouldn't be wasting your time. You should be learning. Cool. So typically, when I talk about optimization, right, we'll minimize a function subject to some constraints. There's sort of three basic words I'm going to use a lot. The first is the objective, right? That's this function f of x is measuring how well I did, right? So I can play this game where I give you an x, and f says like, this is a good x or not. And then we have two sets of constraints, one of which is called an equality constraint, and the other is called an inequality constraint. Hopefully we can see that. So when I analyze optimization problems, there's a couple calculations that just come up over and over again. And even if you took first year calculus, you've no doubt done this, right? So for instance, if I'm trying to minimize f of x, and f of x is just a single, a scalar variable, and I want to minimize this function, then like we're all programmed from birth to like wake up in the morning, take the derivative, set it equal to 0, and find the critical points, because that's how we minimize the function, right? And so essentially, something that's quite important for us, and something you saw a lot of this morning, is computing the gradient of a function. So if f of x, where x is in, I should put this clock down still. If x is in Euclidean like Rn, right, so it has n different numbers as inputs here, then essentially the gradient of f of x is just a big vector where I take the partial derivative in each of the different directions, right, x1 to xn. And thankfully the gradient has a nice geometric interpretation. But essentially, so let's say that I'm minimizing function f of x and x is just on the plane, right? And then I can think of f of x as a height over the plane. Then the gradient of f is, if I'm standing at a point x, the gradient is the direction where I can point my feet and walk uphill, right? And similarly, minus the gradient is the direction where I can walk downhill, right? So like the world's simplest optimization technique would be I compute the gradient, which kind of points my toes down a little bit, take a little bit of a step, and then iterate, and this is called gradient descent. For functions that both input and output more than one number, right? So like f of x goes from Rn to Rm, then I can also compute a derivative of this thing, right? Now it becomes a matrix, right? For every possible combination of input and output variable. And this thing is called the Jacobian matrix. And essentially it's the same thing. It's like a linear approximation of function divide. And then finally, if I compute second derivatives of my function, then no longer am I approximating with a plane, but I'm approximating with a bowl shape, right? And so the matrix of all your second derivatives is called a Hessian. And typically if your Hessian, David, I'm going to get this wrong. Your Hessian is positive definite, and you're at a critical point, then you're at a local minimum, right? Because your function is bowl shaped, meaning everywhere nearby is kind of pointing up. Right? And so the Hessian is something that kind of tells you nearby, what's the closest bowl that approximates my function, or hat, or whatever saddle-shaped thing. Yeah? And usually this information is enough to formulate most optimization techniques. Although there are some fancy third-order things. In fact, I didn't get to you this morning was asking some questions about third derivatives that pop up in some algorithm random. Right, so then our one last little vocabulary word here, which no doubt we've all seen before. By the way, we're totally bored, or this is probably stuff that a lot of you have seen in calculus class. But essentially, the one other point you might need is this word called a critical point. And essentially, this is kind of any time that your function stops, right? So a critical point includes like a point where your function is locally minimized, like this point here, locally maximized, or a saddle point that it kind of slows down for a second and then keeps moving. Yeah? And these points all can be classified as points where the gradient of your function vanishes, right? In other words, like when I get to the bottom of my function, there's no direction I can move that goes downhill because I'm all the way at the bottom, so my gradient is equal to 0. Yeah? That makes sense. Cool. So that's all the vocabulary we're going to need for today. And now I'll tell you a couple simple examples of optimization problems that come up all the time. So, right. So first of all, one thing that's worth noting is that there are a lot of computational problems that even though we don't think of them as optimization problems, maybe when we first saw them, they really can be written that way. So for instance, if I'm trying to solve the linear system of equations ax equals b, one thing I could do would be to minimize the norm of ax minus b, right? And obviously if ax equals b, then the norm of that when ax equals b is equal to 0, the difference. It's called the residual. So this is an optimization technique for solving linear systems of equations. And in fact, techniques like conjugate gradients, essentially, one of many ways to derive those algorithms is by taking this viewpoint and pushing it forward. I can compute, we'll come back to this, but I can compute eigenvalues using the same language. Or, in fact, remember in this totally generic form for an optimization problem, like what I've given you at the top of the slide here, I could even talk about finding just the roots of a function, the zeros, right? If all I care about is finding a point x where g of x equals 0, well, then I could minimize the function 7. It doesn't matter what my function is, I just need to find some feasible point, something that satisfies these two constraints here. So hopefully you guys can understand that this little green box here, it doesn't have very many characters in it, but it fits like a ridiculous number of different problems into it. And this should lead to a question, which is, if I give you an algorithm and I say, you give me f, g, and h, and I give you x that minimizes that subject to the constraints, how well do you think that algorithm will do? Don't all speak at once. Klaus, how well do you think this will do?
Well, it depends on the problem.
It depends on the problem, exactly. So if I'm a snake oil salesman and I come in and I tell you I can minimize any objective with any constraints at all, chances are your algorithm is going to suck. In fact, there are a lot of NP-complete problems that you can write down as optimization problems and look totally innocent, but when you try to actually optimize this thing, you're bound to do quite poorly. And so the one piece of advice, let's say if you get one thing out of the next hour and a half of me and David talking at you, essentially, one thing that you should learn is that you should use the simplest solver first. That is, if there's some generic piece of machinery that just walks down gradients and prays that you're doing okay, chances are, for your very specialized problem, it's not going to do very well. You should take advantage of any and all structure you can in the process of posing and formulating optimization tools. So, in the spirit of that, we're going to kind of work from the bottom up. I'm going to give you simple optimization problems, we're going to make them more and more complicated, and kind of give you a whole hierarchy of different tools you can play with. And in fact, this morning, you guys already saw some of the tools at the very top of the hierarchy. Things like SQP and so on are very advanced tools that can deal with lots of very difficult optimization objectives. But perhaps the simplest one is that I'm trying to minimize some quadratic function, right, like x transpose ax with linear constraints. And if I kind of march through and I take derivatives and I plug in all of, do all of my favorite calculations from calculus class, one thing that's pretty easy to show is that in fact I can derive the global minimizer of this optimization problem simply by solving a linear system of equations. That is, that this top system of equations I've given you up there is exactly the same as solving this thing on the bottom, right? So this is our first example of I can write something in optimization language, but that doesn't necessarily mean that I need a fancy optimization tool to solve it, right? I can use Gaussian elimination to solve this thing on the bottom. One special case that we all know and love in statistics and geometry and almost any field is something called least squares, where maybe my matrix A is now very tall, right? So maybe, for instance, I'm trying to do regression and I expect that I can fit a line to a bunch of data points, but in reality those data points are quite noisy. So x describes the slope of my line, and I'm going to plug in all these things and see how well they match. And of course, all I can hope to do is minimize the total residual, minimize how much error I made for each data point, and sum these things. But now I have sort of more entries in my matrix than I have unknowns, so I can't invert it anymore. But I can still minimize this thing. And in fact, posing this minimization problem up top is exactly the same as solving this linear system of equations written on the bottom. And this thing is called the normal equations. And something that's worth noting is that, and something that we actually neglect a lot in geometry processing, is that if you have derived your linear system of equations by solving least squares, chances are you should use a least squares tool rather than solving the system of equations. It's actually usually quite ill-conditioned, so it can be difficult to solve using the generic tools. So, as one simple example of this that conveniently we already saw this morning in the mapping talk would be if I want to embed a three-dimensional mesh into the two-dimensional plane, right? So I want to map this thing into the plane. Then one of many ways to describe this sort of Laplacian technique that we heard about this morning is just using least squares language, right? So let's say that I have a mesh and has a bunch of vertices. And I can describe, as I smash this mesh into the plane, I'm going to describe the position of vertex I using a variable x sub I. Right? Now, what defines a good embedding of my triangle mesh into the plane is one where if I'm close by on my triangle mesh, and I map these 2 points onto the plane, then they should still be close by when I stick them downstairs. Right? And so I can express that a little more formally by saying I'm going to go over all of the edges of my triangle mesh. Right? So my unknowns are these positions xi for the vertices of my mesh that are getting placed into the plane. And for any adjacent pair of vertices, right, so they're nearby in 3D, I would like them to be nearby in 2D, so I just subtract their positions, and I want that number to be small, so I minimize the norm. This thing is called the Dirichlet energy of my map, but that's just a fancy word for least squares. And right, so hopefully we're all programmed to see that because I'm minimizing a quadratic objective and my constraints are basically linear here, this problem, here the constraints are that like maybe I fix the positions of all the vertices on the outside of the mesh, right? Like I pin this stuff on a circle, right? So now I'm just trying to find where the interior goes. Then I can do this embedding technique, this cut embedding, which is what we heard about this morning, just by solving linear systems of equations. Yep. So even though you might not think of linear systems of equations as an optimization technique, I do think it's worth noting a few things because these probably come up more than anything else in geometry processing. For one thing, there's really never a case when you need to write down the inverse of a matrix. Right? Like, so if I'm solving ax equals b, right, then typically if you take algebra class, you would say, okay, well then x equals a inverse times b. That seems reasonable. But the problem is that A inverse, even if A is like a sparse, well-behaved matrix, the inverse might be very dense and not very nice looking, right? And so typically, rather than writing A inverse explicitly, there are lots of algorithms like Gaussian elimination whose job is to solve a single system of linear equations, rather than sort of find the most generic version of an inverse. And just like I've been telling you about already so far today, essentially any structure that you can leverage that you know about this matrix A can help you a lot in this problem. Right? So oftentimes in geometry processing, this parameter example being one example of this, right, is that you end up with a matrix where essentially you have this entire triangle mesh, and all of your variables are associated with nodes or vertices on this triangle mesh, and your objective terms are just coupling the vertices of your mesh to their neighbors. Right? And typically what ends up happening is when you derive the corresponding linear system, you have a sparsity pattern in this matrix. In other words, the pattern of non-zero values in this matrix more or less follows the pattern of the edges in your graph. Right? What that means is that your matrix is mostly zeros. And you can really leverage that to come up with some very fast solution algorithms that are out there. One of the fastest of which is the character / in MATLAB, which I highly encourage you to try before anything else. But there's all kinds of other properties you can use. For example, if your matrix is symmetric, there are other solvers you can use. If it's positive definite, then there's a ridiculous number of different algorithms out there for solving positive definite systems of equations. And really, these things fall into two classes. One of which is direct solver, right? So if I have like ax equals b, this is going to just start doing algebra on my matrix A until it's completely inverted, and I get the solution of my equation. And these exist both for dense and sparse systems. But sometimes my matrix is so giant that all I can do is multiply by this thing. I can't even write the matrix down. In fact, this happens sometimes. And there's an entire class of linear system solvers that are called iterative solvers that essentially say if all I can do is multiply by A, and maybe if I'm lucky, multiply by A transpose, can I come up with a numerical algorithm that kind of looks like gradient descent and better approximates the solution to Ax equals b. And these include algorithms like conjugate gradients for positive definite matrices, min-res and gm-res for symmetric stuff, and LSQR. I'm not going to try to describe these here because they get a little technical, but I'm happy to fail at describing it to you on the board during the break today. Right. And like I already mentioned, a lot of these systems that you get, because essentially they come from the structure of your triangle mesh, typically they have a lot of zero entries in them, right? Like you don't have long-range communication between vertices on your mesh, and you can really leverage that to come up with fast solvers. Okay, so when I told you about this parameterization technique here, right, I said nearby vertices want to go to nearby vertices, right? Unfortunately, there's a little bit of a lie here, which is what is the best possible parameterization with respect to that criterion? Well, if you think about it, it's just to take your entire mesh and map it to a point, right? Like that's a really, really smooth map, right? It doesn't the derivative is zero. And so the way that we get around that, as you can see in this paper from the Middle Ages, is that you kind of prescribe the positions of some points on your mesh and then fill in the rest. But there's a question which is, can I get away without that? Like, can I force my system of equations to have a non-boring solution inside of it? And the answer is yes, right? And this is one of many ways to understand, right, so this is our little motivation here. And one thing I could do is say that at the very least, I'm going to ask that the norms of all of my xi's, right? Like the positions aren't all 0. And one way to do that would be to just sum up all of their norms and say, well, the sum of all these norms is equal to 1, right? So this eliminates the solution where everything goes to the same place, yeah? And in fact, this is one of many ways to sort of motivate why we care about eigenvalue problems, right? So rather than solving ax equals b for vector x, now I want to solve ax equals lambda x, where x and lambda are both unknowns. Fun fact, this is a quadratic problem. Computing eigenvalues is a non-convex problem. We usually don't think of it that way. Right, so these two things are sort of equivalent, like I've drawn you here. And they're useful sort of when I come up with a matrix that describes some desirable property I would like to have for my output, but the most desirable output ends up being 0, and I need to count that solution out, then essentially eigenvalues are one way to do that. Right, so for example, in parameterization, in this spectral conformal parameterization paper in 2008, essentially that's all they, there's some window dressing, but the basics here are exactly that. They just say, okay, well, if I don't want to constrain the boundary, I'm going to just add a constraint that everything doesn't get mapped to a point, and out comes an eigenvalue problem. And there's one detail here, which is that they also need a second constraint that's linear, and that turns out not to be a very big deal in the scheme of things. Algorithms for computing eigenvalues, they get very complicated, but almost all of them are based on a very simple observation, which is that essentially, let's say that I take a vector and I just multiply by the matrix, and then I multiply it again, and I multiply it again, and I multiply it again. I just keep multiplying this thing over and over and over again. Right? My vector has some component that's parallel to the largest eigenvector. Right? Remember, ax equals lambda x. So in other words, it's scaling by lambda every time I multiply by a. Right? So if I just keep hammering and hammering and hammering away at this thing, what's going to happen is x is slowly going to become more and more parallel to the dominant eigenvector of my matrix A. And this thing is called eigenvalue iteration. And this thing is like the world's simplest algorithm for finding the biggest eigenvalue-eigenvector pair of my matrix. And essentially, built off of this really simple observation is an entire class of different Krylov subspace algorithms, which is a fancy phrase for saying like hammering with your matrix and finding against them. So this is so typically in geometry processing, I don't know too many papers that need more than like either the first 100 or the last 100 eigenvalues of a given matrix. So typically, almost any tool will do here. And once again, sadly, the generic thing built into MATLAB does almost as well as anything else. Right? It's very disappointing for us optimization people to spend all this time worrying about fancy algorithms, and then like the out-of-the-box thing always wins. Anyway, so there are many examples of geometry processing papers that essentially just go back and forth between applying these two little pieces of machinery. One of which that's gotten a lot of attention in the last 5 or 10 years is this idea of a functional map, which is essentially expressing a map between two surfaces, like these two cats here, in a Fourier basis, right? And in fact, if you take a look at that paper, the only real ingredients you need to understand it are exactly what I've given you here. That the first step of this paper is they need some kind of Fourier basis for functions on your surface, and they get that by solving an eigenvalue problem on the Laplacian, which Etienne is going to tell you all about tomorrow. And then they use basically just a least squares kind of thing to find a map that goes from one surface to another that kind of preserves descriptors and commutes with some smoothness. You know? The rest is just detail. In fact, I mean, the rest of this paper has been replaced about 20 different times by papers that have come out. Right, so obviously what I told you are a bunch of optimization problems that all are secretly not really optimization problems. Right? You can solve them using like linear systems, eigenvalue computations, things that you might not have known were really coming from optimization. But there are plenty of problems for which that simply isn't the case. And in general, maybe there's an instance of something called unconstrained optimization. I'm going to remove those second two lines from my generic optimization problem to say, I'd like to minimize a function f with no constraints at all on x. And this happens a lot. So for example, in some of the shape optimization things we heard about this morning, you know, maybe I'm trying to compute a balloon and there aren't really any constraints on, again, I know nothing about balloon optimization. But like maybe I want my balloon to be smooth and I want it to kind of conform to the shape of some triangle mesh and I'd like it to be made of rubber. I don't know why that would be a constraint, but like I can encode all of these things as kind of fuzzy constraints on this variable x, and then I just, or fuzzy terms that measure how well I'm doing. I add them all up together, and I start to minimize. And hopefully what I get at the end of the day is a piece of geometry that I like. Yeah? And there are a lot of things to be aware of in the unconstrained optimization world. Now, as I already described for you, essentially the simplest possible algorithm for unconstrained optimization is gradient descent. Right? So I have some approximation of x as the minimizer. I compute the gradient. Remember, the gradient minus the gradient points downhill. So I point my toes in that direction. I take a little bit of a step. So I just step downhill a little bit, and I eject it, and make myself a little happier. And then I re-point my toes, and I iterate. Right? That's gradient descent. And it's 3 lines of code. It's a good thing to do that. And the gradient descent algorithm is remarkably effective. In fact, it's always effective, because it's just walking downhill with a couple modifications. The first one is you need something called line search, which means as I walk downhill, I didn't give you a detail, which is how far I step, right? And if I'm really unlucky, if I have really big feet, I might step right over the minimum and start going uphill again, right? And so one thing you can do to fix that in gradient descent is to say, okay, I'll use the gradient descent thing to figure out where to point my feet, and I'm going to kind of just shuffle forward until it stops decreasing, and then I'm going to recompute my gradient. And this process is called line search. Line search, you have to be careful with line search algorithms because, in a sense, you kind of have two options, right? I could do a really detailed line search, like minimize over the direction my feet are pointing with like lots and lots of iterations where I just keep trying my thing and going farther and farther and farther. Or I could just take a large step, notice that it decreased a little bit, and then recompute my gradient and start moving in a different direction. And so there's a sort of a push-pull between these two things depending on what you're trying to do. One algorithm that's worth noting is something called accelerated gradient descent, which is sort of a nice procedure for choosing step sizes that doesn't require line search, but for convex functions still exhibits quadratic convergence. I don't have a whole lot of experience with accelerated gradient descent. Machine learning people really like it, but I'm told you to be a little bit careful because oftentimes it's not terribly numerically stable when you're far away from a minimizer, but there's probably experts here that know more about this than I do. Again, I'm here to give you Google search terms, and all these algorithms are easy to try at home. Now, of course, things like line search, gradient descent, I mean, all I'm doing is moving along little line segments, and a reasonable question might be like, can I do a little better if I move along routes? And the answer is yes, and the basic algorithm for this is called Newton's method. Right? So now what I'm going to say is that every iteration, not only do I know the gradient, but I also know the Hessian of my function. And so with all of that information, I can approximate my function with a little bowl. Right? And like I told you in part 1 of our talk today, if I have what's purely a quadratic function, I can minimize it by solving a linear system of equations. Right? So all Newton's method does is it says I'm going to approximate with the bowl, minimize that bowl, and iterate. You know? And this, unlike gradient descent, this thing has quadratic convergence, meaning it gets to the minimum really fast. But it comes at the cost of having to know the Hessian of your function, which might be a dense, kind of ugly matrix to compute. So as we heard about in the last talk, there are algorithms that are called quasi-Newton algorithms, BFGS being one of many, that essentially its job in life is to approximate the Hessian using usually some sparse representation that's easier to store and manipulate and compute. So for instance, in BFGS, what you do is you kind of say, okay, as I do gradient descent, I'm going to remember the last 10 steps that I made. And if you think about it, those are like samples from my function that I've just kind of observed as I've moved around. And then I'm going to use those to kind of do least squares, like a little fit of a Hessian matrix to those data points, and then use that to guide my descent procedure. Yeah? So I would say BFGS is probably the most popular optimization tool in computer graphics, and certainly geometry, because essentially it can deal with any optimization objective. However, given like slide number 2 today, hopefully we all can agree that in fact, when you're using BFGS for your problem and it's somewhat effective, you might then return to the optimization side and say, can I do better? Because this is, again, a very generic tool, so I don't expect it to do great for any single problem. Yeah? Hopefully I've repeated myself. So there's a lot of examples of problems where essentially I just cook up a function f of x that measures all the things I want to be true, and then I minimize it, and out comes the solution I want. One paper, the author of whom is in front of me, so now I'm all nervous, is telling us how to do shape interpolation, right? So maybe I have 2 poses of an elephant, and I'm trying to find the ones in between, right? So one of many ways to do that might be to say, okay, I think that a good shape interpolation is one where the edge lengths kind of interpolate in a nice, smooth, or linear way, and that the dihedral angle, like the little folds between the triangles in my mesh, also interpolate in a linear way. But unfortunately, when I interpolate edge lengths and dihedral angles, I might end up with a bunch of numbers that are incompatible with an impediment. Like they don't actually come with a way to stick those things back in 3D and have exactly those edge lengths and those decoupled angles when I do that, right? And so what these folks do, you can correct me if I'm wrong, is essentially solve an unconstrained optimization problem that says, find me an embedding of my triangle mesh. First, I'll interpolate the edge lengths and dihedral angles to get what I might want, and then I'll solve basically the least squares problem to find a piece of geometry that more or less fits those interpolated values that I just Specifically for nonlinear least squares, there's an algorithm called Gauss-Newton, which, again, remember, we're going to keep leveraging all the information we know. Can outperform, or at least can use less information to optimize pretty nonlinear problems. And there's all kinds of software out there for these optimization problems, right? In MATLAB, there's fmin, UNC, minfunc, and there are all kinds of MATLAB libraries that implement fancy things. In C++, there's BFGS, dlib, and other things. And essentially, they're really nice. I mean, I'm hating on generic optimization tools, but the really nice thing that they do provide you with is essentially you give them a function, a gradient, and maybe it's Hessian, and it gives you back a critical point. And that's very convenient when you're doing engineering, right? And maybe there are two sides to that engineering, right? One is choosing the optimization algorithm, and the other is designing the thing you want to minimize, right? And when you're focused on that second problem, maybe it makes sense to use something like this to just get a rough idea of kind of what your objective wants. Cool. Something we heard about this morning, if you're talking about engineering your objective function, and like that's kind of a nice trick for maybe making your optimization problem more tractable or more smooth, is you can build in something called a regularizer. And in fact, you might even do this just for like your first couple iterations of your problem and then get rid of it just to get a rough estimate. But essentially a regularizer on a variable really roughly is some additional objective term that tries to prevent that variable from going crazy. So for instance, if I add in a little bit of the norm of x, what I'm asking is that x has a lot of small entries. If I add in the L1 norm, like the sum of the absolute values, this is very well known in the world of compressive sensing to give me a vector that's mostly all zeros. So just a couple non-zero entries in it. Those are least squares where you get like lots of non-zero but small things. In the world of like STP and so on, you might want that an unknown matrix as well. This is just to keep in mind. When you hear regularization, essentially all I'm saying is like a bonus objective term in your problem that prevents your variables from going crazy. And similar to this kind of one additional trick that's worth being aware of is something called graduated optimization, where what I'm going to do is I'm going to solve a simpler version of my problem first, use that as an initial guess for a more difficult thing, and slowly refine my solution. Right, so for example, in image processing, maybe I'm trying to align two photographs, and when I look at these two pictures, there's so many little details and you know, for example, stones in this brick house here, that it would be easy to like misalign two stones and get something that looks all right locally, right? And so to kind of get rid of all these local minima, maybe I first blur out these images, align those first, and then kind of remove the blur slowly to refine the estimate. So really quickly, I'll tell you how we're going to add equality constraints to our optimization problem, and I'm going to hand it to David for the next part of our chat today. So far I've told you about minimize a function of f of x without any constraints whatsoever, but maybe there are some things that I want to be true, not in a fuzzy way, like I want them to be exactly true. Right? So for instance, maybe I have some material constraints, or I really want this edge to be exactly length 5 or whatever. Right? So now I want to minimize f of x subject to g of x equals 0. And there are a lot of pictures you can draw. Since I'm not keen in crayon, I'm going to stay in 2D today and show you this in kind of a level set version of this picture. So one way to think about the function f of x that I want to minimize is that it has a bunch of contours that are f of x equals c, right? And so, you know, rather than thinking of it as like height function, I'm going to think of it like, you know, these are all the points where f of x equals 5, and then these are all the points where it's equal to 4 and 3 and so on, right? And so that's these little concentric circles get smaller and smaller as f decreases, right? So the gradient of f points orthogonally, or minus the gradient, points orthogonally downward. Again, this is our big fact for the day. Gradients point down. Minus gradients point down. So, if we have a constraint g of x equals 0, then I can think of that as some curve that's cutting through all of the possible x's. And I'm constraining the point that I compute x to sit on this red curve. Right? So g himself is some function, right? He has a gradient too. But essentially, rather than trying to minimize g, I'm just trying to keep g equal to 0, to stay on that level set. Yeah? But now think about what the gradient of g is doing. The gradient of g is telling me the direction that I can walk that's going to make me violate the constraint. Right? right? Because the gradient is the direction where I change g the most. That's like the direction I don't want to walk, right? So what is true when I minimize f of x subject to the constraint that g of x is equal to 0? If we step back and think about it, is that the gradient of f and the gradient of g are parallel to each other. In fact, they point in opposite directions. I don't know if you guys see this. So essentially, what this is saying is that, remember that minus the gradient of f is pointing in the direction where I can decrease f. Yeah? And the gradient of g is pointing in the direction where I'm going to violate the constraints. So if these two things are parallel, what it's saying is that the only way I can decrease my objective is by violating the constraint, which is bad news. Right? So in other words, when I'm looking for an x that solves this optimization problem, then what I really want is that the gradient of f at x is parallel to the gradient of f at g. So in other words, grad f is equal to lambda times grad g. And this is something called the Lagrange multipliers of the constraint. And you can use it to derive all kinds of fun things. So for instance, if I want to minimize x transpose ax subject to the norm of x equals 1, well, the gradient of f is 2 times a. The gradient of this thing is 2 times x. So at the end of the day, I get this eigenvalue problem, which is exactly what I told you about before. Yeah? So why do we care about Lagrange multipliers? Essentially what they do is they take an unconstrained optimization, or rather constrained optimization problem, right? Like minimizing f subject to g equals 0, and they turn it into an unconstrained root finding problem, right? And this is essentially I'm trying to solve this system of equations for x and lambda. Yeah? And there are all kinds of different ways to solve these constraint problems. But I could reparameterize, like I could choose an x where like just there's no way for me to violate the constraints. So for instance, like if I want to minimize f of x subject to x being on the unit circle, maybe instead I parameterize it by a theta between 0 and 2 pi, and I just can't leave the unit circle. Or you know, I can use all kinds of quadratic approximations like we heard about this morning. Finally, one method that's worth noting is something called the trust region method, which says, okay, essentially, I can try and take Newton's method, like this quadratic approximation I had before, and minimize it, but build in a linearization of my constraint. But I expect that my approximation, you know, I've now taken a quadratic approximation of my objective and a linear approximation of my constraint. So I've approximated the heck out of everything in my problem. And maybe that's okay locally, but if I start going too far, then this is going to become a bad approximation, right? So things like trust region essentially say, I'm going to optimize a little bit. I'm going to step a little bit in the direction that makes this constraint problem happier, and then update my approximation, and so on. So with that, I'll hand it off to David to tell you about some more complicated optimization problems, and additional applications in some of the high-level geometry stuff that we're doing. Any questions?
So Justin told us a lot about unconstrained optimization and also equality constraint optimization. And then in my part now, I want to go a little bit more into the, maybe the most general case of constraint optimization. So at this point, I also want to repeat a little bit, so what are the fundamentals here? So maybe after lunch, it will go too tired in between, so I will restart motivating on these definitions. And most important, I will also explain what's the geometry behind optimization problems. Because one interesting fact is that most of the optimization algorithms are really driven by geometric arguments. And that's very useful here for us because it's a conference about geometry, and therefore I think it's quite easy for you to understand the intuition behind these algorithms without looking at too many formulas. So, but coming back here to this general form optimization problem, what we have this objective function, which Justin already introduced, a function from Rn to R, in the general case, and then we have a set of constraint functions. And now in my case, I want to look at arbitrary inequality constraints. And the good question is, so how can we optimize these, or how can we interpret them? So, what's the geometric interpretation? Justin already had a short picture about that. So, if you imagine a contour with a function g1 of x, that's one of our constraints, equals 0. Yeah, that's what we at an equality constraint. So here 2D is just a curve. Then we can visualize a set of points where the function is less than 0 as just one side of this contour. Right? That's the set of points that is described by this less than 0 constraint function. Or on the other side, if you want the points that are larger than 0, we have the other side. Now, if you want to look at a set of constraints, because we not only have one GI function, we have many, all you have to do is you have to create all these contours and all these points on one side of the contour and intersect these spaces with each other. Right? So if I take two constraints, I get another contour, and I chop off some parts of the points that don't satisfy the constraints. Now, if I do this for all the constraints, I end up with this region that is called the feasible region. So these are, now in this green region, there are all the points left that satisfy all of my constraints. Alright, so now for my optimization problem, I care about what is the objective function. Right? And this we usually visualize as a height field above this feasible region. And since it's gets a little bit difficult to visualize always this height field, we want to visualize everything in the domain of our function itself. And therefore we use this isocontour. So you can imagine that you just intersect this height field with a horizontal plane, and then you get these isocontours that Justin also already showed in one of these examples. We can do this for different planes at different heights, and then we get several of these isocontours, and these can be visualized in the same picture as our feasible region. And now solving our optimization problem essentially just means, yeah, that's a question.
What if the last line is so high that you don't have any more feasible region? Like how would the problem behave?
If you're saying the function goes to infinity or something like that?
Yeah, if the feasible region was collapsing, vanishing,
if the feasible region is empty, then your optimization problem just gives infinity. So there's no points that satisfies the constraints. It's infeasible.
You call it kind of from ill posed. You're giving a computer problem and can't solve, so you can't
Yeah, so if you state a reasonable optimization problem, usually it should be feasible. So now solving this optimization problem just means we want to identify a point in the green region which has the lowest objective value. Right? And in this case, we see that the minimum of the objective function is outside, but the optimal point then will appear there somewhere on the boundary. And then from a geometric point of view, all that we want to do, we have a set of points, and we want to find the point with the lowest function value in this set. All right. A few words on convexity. So, if you want to do optimization in practice, convexity is extremely important. It's something deciding between whether you can efficiently do optimization or not. So, essentially, you can say searching for globally optimal solutions usually requires convexity. Otherwise, you can only solve very small problems. So what does it mean for a function to be convex? To visualize it here. So this means that if I take two arbitrary points on the graph of my function, I connect them with a line segment, and then the function in this segment should be strictly below. Right? So in this case, you can see this here. It's specified by this inequality. So I don't want to talk too much about inequality, but it's just the same as in the visual picture. On the left-hand side, you see an example of a non-convex function. And you already see, so here the graph is above the red line segment, and this is much more difficult to optimize, because what happens is, there on the right picture, you can essentially walk along the gradient, you do all these small steps, and you will always converge to the global optimum. And that's, in general, a statement that you can prove for convex functions, but for non-convex functions, you can have a lot of local minima. You can find these solutions. For an optimization problem to be convex, it's not sufficient that the objective function is convex. What you also need is that all the constraint functions are convex themselves. What this means is, so we have two statements here. So one is about the convexity of functions, and the other one is about the convexity of sets. If all of these constraint functions are convex, this automatically means that also the convex region will be the feasible region, will be convex. And this is again extremely important, because for a convex region, we know that if we take two arbitrary points from this set, then the connecting line segment is also part of the set. And what this essentially means for the optimization problem is that if you want to do some local updates, then if the feasible region is convex, we can never get stuck somewhere on the boundary. Alright, so here's an example for a non-convex feasible region. That's another important consequence. So if you are doing optimization and you want to handle equality constraints, the only way that the equality constraint problem is convex is that you restrict to affine equality constraints. So what's the reason for this? So it's quite simple. I mean, if you want to express in this general form with inequality and equality constraint, you just need two of them, right? So if you want x equals 0, then you can add constraints that x is less or equal than 0 and minus x is less or equal than 0. But now I said I require for all these functions to be convex, which means that gi of x as well as minus gi of x has to be convex. And the only functions where this happens are affine functions. You see here, so if I have such a curved structure, this can never work. What I need is something that's straight, because affine functions are at the same time convex and concave. So from a practical point of view, this means if you want to optimize something with equality constraints that are not affine, then you already know that this is not a convex optimization problem. It's something you know already you're in a class of difficult to solve problems. Alright, and this is my first very important take-home message for you. So if you want to do optimization for one of your geometry processing problems, then always search for convex formulations, because those are the problems where we can find the global optimum efficiently. I think in many of the talks next week, you will see that people talk about certain optimization problems. And so what are the procedures to end up with a convex formulation? I mean, you could naively start with just writing down your optimization problem and then prove whether it's convex or not. But then there's a very high risk that you end up with a non-convex formulation that you can not optimize efficiently. So typically what people do is they go the opposite way, that they already design the problem that it fits into a class where you know that the full class is convex itself. And I want to discuss some of these important convex problem classes, where for sure next week you will see several of these. The first one is, maybe many of you already saw, it's a linear program. This means that in this case, our objective function as well as all constraints are just linear functions. So here h transpose x for the objective and a matrix a times x less or equal to b for the constraints. How does this look like geometrically? A linear objective function means that the gradient is constant everywhere. So if I plot this as a height function, I just get a kind of gram, which is here color coded. Then for the, or if I look at these isocontours, I just get parallel straight lines. The linear function with the gradient A transpose. Now if I look at the inequality constraints, so each inequality constraint is an affine function which defines a hyperplane. So we're talking here about a set of half spaces. If you intersect all these half spaces, what we get is a polyhedron. So from a geometric point of view, solving a linear program means we want to find the best corner of this polyhedron. Why a corner? I mean, you can easily see if I have a polyhedron and I have a linear function, then there's always an optimal point, which is a corner of this polyhedron. Because if it would happen that the gradient aligns with one of these sides, then of course you could choose one optimum which is on the side, but you can also always choose the corners themselves. This motivates some algorithm like the simplex method, which just walk from one corner to the next until they find the optimal solution. Alright, so linear programs sound to be very restricted, right? We only have linear objective functions, we only have linear constraints. I want to give here some examples why they are extremely useful in practice. And the first one is the so-called Chebyshev center, where you have given a polyhedron, and now you want to identify what is the largest ball that fits into this polyhedron. Let's see how we can formulate this as a linear program. So first of all, consider the question, what is the ball, or which balls fit into a half space if you have given a radius r? And this is quite a simple question. I mean, you just need to have an offset of R to the boundary of this half space, right? If you look at the picture here, I think it's easy to see. And this can be formulated as a linear constraint, because this offset appears with the, so we want to optimize for the radius of the ball, but this vector A is just constant. So we get a linear constraint here. Now, for the polyhedron, we just want that the ball is inside of several of these half spaces, which means we just get several linear constraints. So in total, we get a linear program to find this Chebyshev center, which minimizes minus R, just means we maximize the radius of the ball, subject to all these linear constraints, which contain X, which is the center of the sphere, and R, which is the radius of the sphere. And this is a linear program. Alright. Linear programs are also extremely useful for certain kinds of reformulations that you will always see. So Justin already motivated that often we want to do kind of regularization where we add some, let's say, one norm terms or infinity norm terms. And I will show you that working with one norms and infinity norms can always be reduced to linear programs. So why is this the case? So let's say you have an affine function like ax minus b, and you want to look at the one norm. The key insight here is that the one norm itself actually is the maximum of two linear functions. And these are, so if I want to have the one norm of x, this means just the absolute value of x, and this is the same as the maximum of x and minus x, both being linear functions. With this insight, what I can do is I can take each one norm term of my optimization problem, introduce a new variable y in this case, and then require y to be larger or equal than my one norm term and larger or equal than the negative of the one norm term. Because this gives me exactly the following, that this newly introduced variable is larger or equal than the maximum of both terms, which is the absolute value. Now you could say, okay, well, I know that yi is larger or equal than the absolute value, but I want to minimize the real absolute value and not something that is larger. But this is automatically handled by the optimization problem itself, because overall this yi term just appears in these two constraints, and if we minimize it, it will always shrink as much as possible. And in the end, yi agrees with the absolute value itself. Alright. Almost the same trick works to optimize infinity norms. So maybe you don't know what the infinity norm is. It's if you have a vector, you just look at the absolute value of the largest absolute value in the vector. That's the infinity norm. In this case, you can do the same trick, but instead of introducing new variables for each absolute value term, you just introduce one. Like stated here, because then in the end, this variable will be larger or equal than the absolute value, the maximum absolute value of your problem. So these two tricks are used a lot in practice to handle one norms and infinity norms. Very related is the following LP reformulation, where you want to work with a piecewise linear function. So imagine your objective function has such a piecewise linear shape, all these line segments, and you want to minimize that. Here the simple observation is that this is again the maximum of a set of linear functions. And so you can again write it as such a linear program, minimization program. Alright. So this is about linear programs. This morning in the course we already saw quadratic programs. So all linear programs are for sure convex. Now I'm going to the next class, which are quadratic programs, which are also always convex if this matrix Q is positive semi-definite. So if you can write your objective function as x transpose qx plus pre transpose x plus c, and Q is a positive semi-definite matrix, then you have a quadratic program. In this case, the isocontours of your function are not straight lines anymore, but these are ellipsoidal curves here in the plane. For a quadratic program, something you have to take care of. It doesn't mean that the constraints are quadratic, so they are still linear, which means that we still optimize on a polyhedron. The biggest difference compared to linear problems is that now the minima can also appear anywhere on the boundary of the, or actually anywhere in the feasible region. So you're not restricted to corner points, which requires different algorithms to solve quadratic programs. Here's one example, also from geometry processing. So if you want to compute the distance between two polyhedra, which means you want to identify one point in the green region and one point in the red region, such that their distance gets minimized. This can be formulated as a quadratic program in a straightforward way. So we already saw that restricting a point to a polyhedron, these are just linear inequalities, right? So I have two sets of constraints. One saying that the point P is inside the green region, and the other part of the constraint says that the point Q is inside the red region. The distance would be the square root of the quadratic function, but due to the monotonicity, you could just square it, have a quadratic objective function, and so finds the distance between the two polyhedra. All right. The next class of programs that I want to talk about are second-order cone programs, and they are indeed a generalization of both previous ones. So you can show that linear programs are a subset of quadratic programs, which are a subset of quadratically constrained quadratic programs, and they are all a subset of second-order cone programs. Which seems to be a little bit surprising, because here the objective function is a linear function. But there's a trick that you can move the objective function into the constraints, like we did with the LP reformulations. But let's have a look at the structure of the second-order cone programs. So what we get here is a new type of constraints, where you have a square root of a quadratic function, which is less or equal than a linear function. So how can we visualize that? I have a simple example where, so here's one constraint like this. You take the square root of x1 squared plus x2 squared is less or equal than x3. And the geometry that is formed by this feasible region is such a cone. It's called second order cone, or sometimes ice cream cone for some obvious reasons. And why does this happen? I mean, if you take the square root of x1 squared plus x2 squared, this describes a disk. Right? If you say this is less or equal than r, then you have a disk of with radius r. Now, since x3 is an additional dimension, what happens is you just stack these disks with growing radius on top of each other, giving you such a cone. Just from the picture, you can see that this region is definitely convex, and these second-order cone programs are also used a lot in practice. So I have one example from the geometry processing community, which is about computing bounded conformal distortion mappings. It was presented by Jan Lippmann in 2012. And the problem is the following. So we want to look at deformations of triangles. So given one triangle here, we want to look at such deformations. But we want to formulate constraints that excludes deformations where the angles get largely distorted. Or we also want to exclude deformations where the orientation flips. The full problem, unfortunately, is a non-convex one, but there's a quite nice approximation with second order cone program that works well. And so let's look at an example. Let's imagine we take this gray bar, and now we want to deform it in a way where we move around the green points, which are control points, and get a smooth deformation. I think this morning you learned a lot about mapping, so if you just compute a conformal mapping without any additional constraints, you get something which is highly distorted at one of these constraints. Everywhere else it looks nice, but you really concentrate on all the distortion there. If you add such bounded conformal distortion constraints, you get something which, on average, is more distorted, but you don't get this concentration anymore. And that's the difference between solving an unconstrained optimization problem where you just minimize the distortion, the average distortion, or this constrained optimization problem where you minimize the distortion subject to an upper bound on the conformal deformation. All right. One last class of convex optimization problems that I would like to mention here, which also used a lot in practice, are semi-definite programs, SDPs. So we are now working here in matrix space. So X is now a symmetric n by n matrix. We are optimizing a linear function in this space, which can be fancily written as, you can write it as a trace of C times X, where C is a coefficient matrix. Here. But what this actually means is that you just compute the sum of coefficients from the C matrix times the entries of the X matrix. So it's just a linear function in metric space. Right? We take linear inequality constraints in this metric space. So again, trace of AI times X less or equal than BI. And the interesting part is here that we add one extra constraint, which looks quite complicated. It's X less or equal than 0 with this rounded inequality sign, which means that the matrix is required to be positive semi-definite. And this turns out to be a convex optimization problem. All right. So these are the problem classes where if you want to do efficient optimization, you should try to model your problem to fit into one of these classes. So the next question is, once we have such a convex problem, how can we find efficiently the minimum? So for these constraint optimization problems, there are some first order optimality conditions that are necessary. You already saw a preview also this morning in the talk. Let me recap this a little bit. So these optimality conditions are based on the so-called Lagrangian function, where you take the objective function and sum up all the constraint functions multiplied by additional variables lambda I, which are called Lagrange multipliers. So for this Lagrange function, we can formulate the optimality conditions for a minimum X star. These are called KKT or Kerr-Tucker conditions. I will first just list them and then explain what it means geometrically. So the first one is called stationarity. What you do is you compute the gradient of your Lagrangian with respect to X, and you say this gradient has to vanish. The second one is prime feasibility, which simply means that all your constraints need to be satisfied. The second one, which is not so obvious, is dual feasibility, which means that for the stationary point, right, where the gradient vanishes, we get some lambda I variables, and all these lambda I variables need to be positive. So that's a very important aspect. So I will explain in a minute what this means geometrically. So you should really pay attention. And the last one is complementary slackness, that from these terms, from the constraint functions, which we multiply with the Lagrange multipliers, all these products have to be 0. So what does it mean? First of all, you should observe that if you don't have any constraints, all these KKT conditions just reduce to the usual gradient f of x equals 0 that we know from the unconstrained case, right? Because there's no prime feasibility, we don't have any variables lambda, and therefore 2, 3, and 4 disappear. If you have constraints, then you should imagine the following picture. So now you have such a minimum point x star, right, which is here on the boundary of constraint, and now we can distinguish two different cases in these KKT conditions. First of all, we should recall these Lagrange multipliers that we had from the equality constraints. So we said here, if you find an optimum point for an equality constraint, what happens is that the gradient of the function is exactly opposite to the gradient of the constraint function. Or the right interpretation here is that the constraint function creates a force that prevents our point x star to move closer to the minimum. Right? So there's a kind of barrier. So we create artificial forces that influence our movement. So if this happens, then we create an artificial force, we call such a constraint active. since we don't have an equality constraint, these artificial force will always point to the inwards of my feasible region, right? Because if the point x star would like to move inwards to the green region, I don't need an artificial force because there all these points are feasible by construction. So I only want to create forces that point inwards. And that's the condition that we have here in number 3, the dual feasibility. So these lambda coefficients, which are essentially the forces, need to be positive, pointing in one direction. What we also see is that in this case, if we create a force, we are on the boundary of the domain. Right? So the corresponding constraint function itself is 0, and this explains the complementary slackness. So if I create a force lambda I, which is non-zero, then the GI function is 0. We look here, 0.4. So these are the so-called active constraints. Then we have inactive constraints, which in this setting here don't matter at all. So for the green constraint curve, at the current point, we don't need any artificial forces. So the number terms are just 0, and the constraint function itself is negative. All right. Once we find such a point which satisfies these KKT conditions, we know for a convex problem that this is the minimum. So let's look at the first algorithm, which directly tries to satisfy these KKT conditions. It's called the active set method, and the main idea is quite simple. So we want to use the algorithms that we already know from unconstrained optimization. And we can do this in a way where we say, okay, we do first unconstrained optimization, and then we create a set of equality constraints. Because we know how to do unconstrained optimization, we know how to do equality constraint optimization, since Justin told us how to do that. How can we use this in our active set method? So we start from a feasible point, x0. While the KKT conditions are not satisfied, we optimize with all equality constraints from our active set, which initially is empty, which would mean that we take such a red optimization path. At the point where we would violate one of the constraints, then we add it to our active set, or we activate it. This means we just walk to this step, to this point x1, then we activate this blue constraint here, and we continue with an equality constraint, or with an optimization problem where we have one equality constraint, so we're just moving on this blue line anymore. Then we get to the point x2. And now this is the most important part of the algorithm, because at this point, now we would violate another constraint, and here in our 2D picture, now we would be stuck, because if we have two equality constraints here in 2D, the point is determined. At this point, we have to the KKT conditions are not satisfied yet, because the artificial force that we are creating from the first constraint is actually pointing to the inwards of the feasible region from this constraint, which means that this artificial force is negative instead of positive. And this tells us in the active set algorithm that we have to deactivate our constraint or remove it from the active set. So, which means that now only one constraint is left in the active set, we continue optimization, and in this simple example, we find the optimal point. Alright. What you can see is that these active set methods, they always have a very characteristic way of converting to the optimum. They directly go to the boundary, and then they just walk along the boundary by activating and deactivating these constraints. There's one aspect that I didn't explain yet. I said we will start with a feasible point. And that's something that we always need for active sets methods, but how can we actually find that if we don't know any point that is already in our feasible region from the beginning? And this is done by the so-called phase 1 feasibility problem, and this is another optimization problem. So I just say, okay, I want to minimize the new variable t such that subject to gi of x is less or equal than t. So what you can see is that from my original problem, I want t to be less or equal than 0, right? So if I minimize t, if I reach a point where t is 0, then I have an initial point for my problem that I started with. Okay, now you might ask, this sounds a little bit fishy, right? So I say I want to do constraint optimization to find the initial point to actually solve constraint optimization. So that's yeah, a little bit strange. But in this case, the reason why we do that is that finding an initial point for this feasibility problem is extremely simple. Because all that I have to do is I initialize my new variable t just with the maximum of the constraint violation for my initial problem. Here, if I choose t0 to be the maximum of gi of x0, I have a trivial initial point for my feasibility problem. And then I can use the former algorithm to find the initial point, and then solve another constraint optimization problem to find the actual solution. What this geometrically means is that, let's say we have an initial point that is outside the feasible region, then I add this t parameter, which enlarges the feasible region to get an x0 which is inside. And then while solving this problem, actually we shrink the feasible region again back to its original size or even smaller, and we can stop as soon as we found a t that is less than 0. Alright. A few properties of this active set method. So the one that I showed here just gives you a very rough idea of what is going on. So there are many sophisticated variants. So you will, if you look into the literature, you will see primal methods, dual methods, primal dual methods. This always relates on how you do each iteration in your optimization procedure. So what I showed to you is a pure primal method, which means that we always update the x variables of my original problem, mostly. In the dual methods, you work a lot in the space of your lambda Lagrange multipliers. And primal dual methods then optimize everything at once. There are also many specializations for linear programs, for example. The simplex algorithm belongs to the category of active set methods. So for those of you who know the simplex method, if you move from one corner to the other, this essentially means that you deactivate one constraint and activate another one. These active set methods are usually a good choice if you only have few constraints in the optimization problem, because then usually you need only a few iterates with activation, deactivation until you find the optimum. They're also good if you want to do a Bommes start, which means you want to solve a series of related problems. So imagine you have a problem where your objective function changes a little bit in every iteration. Then you can expect that your solution from the previous step is already a very good guess for the next optimization problem. And this is called the Bommes start. And you want it to converge fast, and for these active set methods are particularly well suited. There are also disadvantages. For some problems, you really require a huge number of iterations. Right? In particular, you can imagine if the boundary of your domain is very complicated and has lots of small segments on the boundary, then you have to activate and deactivate a lot of constraints, which means you have to do a lot of iterations until you find a point where the conditions are satisfied. There's another method that I would like to introduce here, which is the interior point method, which we will see has completely different characteristics from the solution point of view. And here the idea actually is very simple. So the key idea that we use here is called, or what we need, the key ingredient is the barrier function. That's why the method sometimes also called the barrier method. What's the barrier function? It's a function which is just strictly 0 if we evaluate it at a point u less or equal than 0, and then it immediately jumps to infinity for all u values that are positive. It's depicted here. Why is this useful for our constraint optimization? Well, we can use it to turn our constraint problem into an unconstrained one by just overwriting the objective function value for all points outside the domain with infinity. And this can be done by just adding this barrier function evaluated on the constraints to our objective function. And in this case, now our original constraint optimization problem is equivalent to this unconstrained one on the right. Great. So now you would think, okay, cool, now I can use just gradient descent and I'm done. But be careful. I mean, the optimization problems are equivalent, but the right one with our barrier functions is not differentiable. So things like gradient descent don't work out of the box. So we have to spend a little bit more effort to make this work. So there are many different approximations of the barrier function that help us here. The most common one is the logarithmic barrier function, which is a smooth and convex approximation infinity function. So it's minus 1 divided by t, the logarithm of minus u. And there's one new parameter t, which can be chosen rather small. Then we get let's say a very smooth but rather bad approximation of the barrier function. Or if we choose t larger, we get closer and closer. The question is, how do we want to choose t in practice? You might say, okay, I want to choose it very large, because then I get a better approximation. But the problem is that the curvature in the corner gets larger and larger. And the convergence of our unconstrained optimization problems depend a lot on this curvature, or on how large higher order derivatives are. So from a convergence point of view, it would be better to choose a small t value. And what the algorithm does actually is it starts with a small value for t and then increases it slightly. So what we do is we iteratively solve these unconstrained problems where we add the barrier functions. We start with a small t and then increase it until we get a good approximation. And you can indeed prove for convex problems that m divided by t is the tolerance, the maximum deviation that you get from the optimal value. So what is m is the number of constraints, and t is the parameter of the barrier function. So if you want, let's say, accuracy of 10 to the power of minus 6, then you already know up to which t value you have to do this iteration. Okay, so now let's look at how the solution procedure would look like. So we're starting again from feasible point x0. Then we compute an x1. In this case, this will be very close to the center of our feasible region. Because if you look back at this logarithmic barrier function here, you see that inside the domain, it is not zero, actually it is decreasing. So this means if you choose a small value of t, you will find a solution that is as far as possible away from the boundary of your feasible region. And that's what we see here. So we start with a small t, so we find a point that is somewhere close to the center of this feasible region. Then we reduce the value of t, converge a little bit more to the boundary, and so on, until we find the optimal point up to a certain accuracy. So compared to the active set methods, we immediately see that now we don't walk along the boundary, but we take a so-called central path. We go to the center and then slowly converge from the interior to the boundary. And only in the end we really touch the boundary. While the active set method directly went to the boundary and then did most of the work along the boundary. Okay, also for interior point methods there are many sophisticated variants. Again, primal, dual, and so on. But what you can also do is you can more smartly choose the adaptation of t. So here I said, okay, we start with small t and then we just multiply it by 10 up to a certain accuracy. But from your optimization problem, you can deduce some information which gives you more clever strategies to get an even faster convergence. There are also many specializations for certain classes of problems. I don't want to go into detail here. Let's talk about when are interior point methods a good choice. They are very good if you have large-scale sparse problems with many constraints. Right? So many constraints means a complicated boundary. But since we are not worried about the complexity of the boundary, because we're just converting from the interior, it does not hurt with interior point methods. They are also pretty good if you have a non-convex feasible region. So often they can still find a global optimum, because so non-convex feasible region is problematic if you would walk along the boundary, because then you might get stuck. But if you come from the center, it's very likely that you still converge to the, let's say, right non-convex part of your feasible region that you're searching. So of course there are no guarantees, but if you have something which is a non-convex feasible region, I would definitely recommend you to use interior point instead of active set. There are also disadvantages. these interior point methods are not very good for warm start, because even if you have an initial point that is already, let's say, already your optimal point, since you start with a small value of t, you would move away from this optimal point to the interior of the domain and then converge back. And so you don't really easily benefit from having a good initialization. All right. So these are quite traditional algorithms. There are some more algorithms that Justin can tell you about. Do you have time?
Do you have time? Tell me.
So we also want to talk about discrete optimization. Okay. Maybe we skip this part and then you will see this in the slides. Right? Or we can upload. So is it planned to upload all the slides?
Yeah, sure.
Okay. Because there are some algorithms that are not as general as these, but they turn out to be very efficient for specific problems that were used in geometry processing or also in computer vision. Okay, so the next part of my talk is about mixed integer optimization, which is also constraint optimization, but in a different flavor. So in the continuous setting, we said, okay, we have a kind of height field over our domain, and we want to find a global optimum or local optimum, but we can always do some continuous updates in our feasible region. So, which means that our optimization variables are continuous. They are from Rn. In mixed integer optimization, what we want is that we also have some degrees of freedom that are discrete. And here on my slides, the yi variables, they are allowed to be only integers. So it's another constraint. And you see in the 2D example, what happens if I have one continuous and one discrete variable, then the domain where I optimize actually gets into these sliced curves. And these are very different optimization problems, right? Because let's say you're on one of these slices and you compute a gradient that points to one of the other slices. You cannot just do a small step. You can just jump from one slice to the other, but there's nothing in between that would be allowed. And this already smells like there's a kind of exponential complexity, because what you could do is you could just enumerate all discrete choices and then solve a continuous problem in one of these stripes. But we're talking here about problems in n dimensions, so yeah, exponential complexity in n dimensions is really, it's not a good choice. So let's say if you have a one integer variable, you might consider the solution, otherwise you would wait forever doing that. But there's another way what we can do, and that's what I want to talk about here. So you saw already in the previous part that to do constraint optimization, actually we use the tools from unconstrained optimization. And now we want to do a similar step where we want to use the tools from continuous constraint optimization to perform this mixed integer or discrete optimization. And I want to explain a little bit here in the case of an integer linear program with these integer constraints. So let's visualize that. So remember, for just a linear program, we have a polyhedron as a feasible region. We have these linear isocontours, and we want to find the minimum. Now, if we solve it as a mixed integer problem, in this case where we require both variables to be integers, then this means that our feasible region are only a set of points, and exactly these green points which are inside the polyhedron. And we want to identify those with the lowest objective function value, which in this case would be this one. How can we do this? By solving a series of continuous problems. So the most prominent class of algorithm for this is branch and bound. And the main idea is that we say, okay, initially we don't know anything, but then we want to compute a lower bound of our optimal solution and an upper bound, and then we want to increase the lower bound and decrease the upper bound until they get equal, and we can prove that it bounds optimum. And we want to do this by solving a series of continuous problems. So how can you do this? What we need is a continuous relaxation of our problem. And in this case, it's easy. We just say, okay, we have some integer constraints, but who cares? We just ignore them, right? So then we're back in the setting of a continuous problem, which is called the relaxed mixed integer problem. And this immediately gives us a lower bound, because our feasible region is larger. So if we solve this continuous problem, we find a solution, but we know that the mixed integer solution can never be better, because the feasible region of the mixed integer problem is just a subset of these points. So great. So we have a way to increase the to get lower bounds. But what we also need is we need to get an upper bound, and we need a procedure to improve our bounds. And this can be done by the branching. And so what we do is we first solve our relaxed problem. It's just a continuous problem. But then what will happen is that one of our y variables, which should be discrete, of course will be continuous. In the algorithm, we identify one of these variables. This yields somewhere on the real line, but it's only allowed to be one of these integers. And we identify the integers which are the next one, or the next lower one, and the next higher one. And then we create two new subproblems. And what this actually means is that we cut off this continuous region in between these two integer values. And we can do this by creating a new instance where we add one linear inequality constraint where we enforce the variable yi to be less or equal than the truncated continuous version. You can already imagine that in this new problem, if I have this inequality constraint, the best solution was this red bar in the middle. But now, if I restrict to the blue bar, for sure it will end up on the boundary. So it will, although it's only a continuous problem, it will become an integer. But if you only look at the blue problem, then we would have excluded all larger values. So we also need to create another instance where we look at this part of the domain. The right one here. Okay, and that's a branching. And you see that what happened here is we started with one problem, but now we have two problems. So it's also a kind of exponential complexity in creating these kind of problems. But what you can also see is that by doing branching, we always improve the lower bound, because we removed the current minimum or the current best value for the yi variable. We removed this continuous section in between the two integers. So the new best value that we can get from both of these problems will be higher. So we grow our lower bound. Okay. Then here in the branch and bound algorithm, so we have active nodes, which are problems that still need to be solved, right? So you saw we have one problem, then we split it into two, and then this node is finished. But now we have two new problems that we need to solve. From these two new problems, the lower bound is always the minimum of these continuous problems that still need to be solved, right? That's the best information that we know what is or how low the function value can get, the objective function. If we continue this procedure and we branch more and more variables, in each step it's very likely that at least one of these variables becomes an integer. So at some point, although we are solving these continuous problems, we will end up with a solution that is feasible for our integer problem. That's such a feasible node. In this case, we get for the first time an upper bound, right? Because now we have a feasible solution, we have an objective function value, and we know that the best integer solution, of course, can only be lower. It's an upper bound. And this is very helpful, because in our branch and bound tree, if we now come to a point where our continuous solution already has a higher function value than the best solution that we already found, we can prune the subtree. Because we know that if we go deeper in the tree, the objective function value can only increase. It will never get lower for convex problems. And that's the reason why these branch and bound algorithms, despite they have theoretical exponential complexity, can be very fast in practice. Because for many of these things, we never have to compute the solutions. All right. And then, so we can terminate as soon as we know that the difference between the upper and the lower bound is smaller than epsilon. Then we know, maybe we didn't find the best solution, but we were very close. And And you can easily prove that if you have a convex problem, or if when the relaxation of the integer problem is convex, then this branch and bound algorithm will always give you the global optimum. In this algorithm, there are two ingredients where you have some degrees of freedom how to choose them. One is the node selection strategy. Right? In your tree of active problems, where you have to somehow decide where you want to continue. One obvious strategy is depth first, that you say, okay, I take the node where I'm already deep in the tree, because there it's very likely that I already have many integers and I continue there. But you can also do the opposite. You say best first search. This means you're more like a breadth search, because then you take the solution where you currently have the smallest lower bound, the smallest value of a complex relaxation, and you want to push this lower bound. So you want to split this problem into two new where the lower bound improves. So the depth first actually pushes the upper bound, and the best search first pushes the lower bound. And then there are some dynamic characteristics where the algorithm decides on the fly what's the best nodes to choose. And there are a lot of heuristics, and I think the best ones are not even documented. So only if you want to apply such a branch and bound algorithm, the best ones are commercial, like Kurobi or Cplex. They're extremely expensive. So I think one license is $10,000 or something like that. And it's because these people invested so much time in finding good heuristics that work for practical problems. Selection strategies. The other ingredient is a branching strategy. So once you selected a continuous problem, then you also have to decide which non-integer variable you want to branch. There are typical choices: maximum infeasibility, which means you take the variable that is most undecided, so close to 0.5. So let's say if you have a variable that's 1.5, then it's completely undecided whether it wants to get 1 or 2. And why is this reasonable? Because that's very likely that your lower bound will improve a lot, right? Because this variable has to change a lot. But this is only an estimate, because you don't know exactly how changing the variable will translate into the change of the objective function. If you want to do it correctly, this is called strong branching. There you would really search for the variable which improves your lower bound in the best way. The problem here is that it's extremely expensive to compute, because you would have to solve continuous problems for all candidate variables to just decide which variable to continue on. Therefore, what people often do is they use pseudo-reduced costs, which is an approximation of strong branching where you learn from the history what are good choices. And again, here are also dynamic heuristics. Okay, so let's look at one example of this algorithm, because here, so far I presented the algorithm just in its generality, and let's see how it works on our integer linear program. So we start with a relaxed problem, which means that we just find the minimum of our continuous problem, which is there on the corner. It's not an integer yet. This means we have to split in this variable. In this case, we can split the domain in two ways. So we can either truncate or we round to the next integer, which gives us two different feasible regions. So if we intersect it with the green region, here on the left one, we already see that the constraints become infeasible. There's no feasible point left. So there we can already stop in our tree. Then we look to the other problem. We add this inequality, which shrinks our green domain, and then we find a new continuous optimum, which is an improved lower bound. Okay, so now we have one active node, and we continue again. This time we branch in the other variable, the y variable. Gives us two new problems. We start with the lower one. In this case, we see here that we find another y star for this continuous optimization, but it's still not finished. On the other side, we find this one, which is the first time a feasible point. Right? This is on the integer grid, which gives us an upper bound. And what happens now is that in our in this other node that we still have to proceed on, we see that the continuous optimum has already a higher function value than the best feasible point that we found. which means that at this point here we can just prove the rest of the tree, and we have proven that we found the optimal solution. So in this case here, by solving 5 continuous problems. Alright, so this brings me to the end of this course. So let's summarize. We saw, or you in particular will see in the next week, that there's omnipresence of optimization in geometry processing. So I think nowadays it's really important to understand some basics about optimization to follow what's going on in the community. We talked about unconstrained optimization, equality constraint optimization, inequality constraint optimization, and mixed integer optimization. So these are all broad classes, and in this course we wanted to give you a rough overview, that you see some examples, you get a kind of intuition which classes exist and what you can do with them. Very important is convexity. So I told you, if you want to do optimization in practice, search for convex formulations. Of course, we could not cover everything in our course here. If you got interested, we will publish the slides, but even more important, look at some of the good books. I think 2 of them were already advertised this morning. So I really like the Convex Optimization by Stephen Boyd. It's a very instructive book and everything very well motivated. The one from Knockedal and Wright, the numerical optimization, is also very good. It dives more into the details of certain algorithms. And if you're interested in discrete optimization, then I would recommend you the integer and combinatorial optimization by Nemhäuser and Olsey. I think the first 2 are available online, the third one. I also want to talk shortly about some software packages, because what happens in practice is usually you don't want to implement these algorithms yourself. There are very good software packages, like the Eigen library for linear algebra. Then there is the IPOpt library, so it's a very fast interior point method that also works pretty well for non-convex optimization. We recommend this one. Mosaic is one that is really good for convex optimization problems, also for SDPs. Gurobi is a commercial mixed integer optimization solver which implements all these nice heuristics, so it's extremely fast. So if you have some discrete or binary problems, you should try this one, or the one which is very similar. It's called Cplex from IBM. Actually, usually what happens is if one of these 2 publishes a new version with some new features, and a few weeks later the other one gets the same. So I think also the developer groups, I think the Gurobi library emerged from a sub-team from the Cplex that started a new company. So it doesn't matter which one you choose. MATLAB is another solution that many people like, to particularly to prototype algorithms, because you have a large toolbox of algorithms, and compared to the previous one, it's sometimes easier to try this algorithm without setting up a complicated compilation framework and so on. Then there's a CDX software. It's from Stephen Boyd, from the author of one of the books. It's also nice to prototype some convex optimization problems. And last but not least, it's here on the slide, the Comiso library, which is a library that we developed in Aachen, and yeah, it has some own solvers inside, but it also offers a unified interface to all of the other libraries that I discussed before. So if you don't want to decide right from the beginning, then this gives you one way of implementing your optimization problem in a general form that can just then be solved by any of the other algorithms. Okay, so we're coming to the end. Thank you for your attention.